In this video, we begin the discussion of another probability distribution, and it's the normal distribution. That's its name. You'll hear people call it the bell curve, but it is the normal distribution. It occurs a lot naturally. In addition, we make a lot of assumptions in statistics that rely on the underlying distribution being normal. And so it is an incredibly important distribution to know how to use. We'll do an example later on the central limit theorem, but let's talk about what it is. First of all, it looks like a bell-shaped. It has two parameters that completely characterize it. When you say something's normally distributed, that's not enough information. You also need to determine, also need to know where the mean is, and that's the middle, and also the standard deviation, which tells you how much variability, how far are the tails away from the mean. And let's look at one and kind of work our way through. I've got in Excel, I've set up a normal distribution over here. And in this case, I've got, so this is the bell curve, and if you notice what happens, it's centered at the middle, so that the mean is 10, so it is centered. The top of this is centered. It is a symmetrical distribution. It looks the same. If you would fold in half on the mean, it would look the same on one side or the other. Even though it's hard to tell, these tails never actually touch the horizontal axis. The value gets closer and closer to zero as you move either way, but it never actually touches the horizontal axis. Well, let's play with these numbers a little bit. What the mean does is tells you where it's centered. So right now it's centered at 10, but if I change that to 12, look what happens. It scoots over, now it's centered at 12. I can move it over to 15, and again, I've limited this graph to just a little bit of numbers, but if I could scoot it over, and it can take on any value from minus infinity to infinity. It can be negative. It can be centered at 0. It doesn't really make sense in my graph because I'm not showing negative numbers. But you could certainly center it at 0, and then it would look the same on the other side of 0. So that's what the mean does. It tells you where it's centered. Well, what does the standard deviation do? Remember, standard deviations measure variability, and what it's telling you is how far are the tails away from the mean. So right now I've got it at 2.5. Let's make that really small. Let's make it 1. And all that means is that we have less variability. There you go. The tails get closer to the middle. If I even go even smaller and almost make this like nothing, you're going to wind up getting a straight line. If I make it really large, it was 2.5 to start with. Let's make it 4. You can see it gets wider. If I make it really wide, we'll kind of make it silly and make it 10. It gets really wide. And again, it's still centered at the middle, but because of the variability, we're getting a wide number of values. Now, what does that mean? So what that represents is that if we had a process, let's say this is assembly time it takes to fix something, to assemble something, and we knew it was centered at 10 with a standard deviation of 3, that means that we would take on values anywhere from close to where this tail gets close to 0 all the way over to this one. So it looks like in this example that we can get values anywhere from 0 to 20 centered at 10. If somehow we could improve the quality and get more consistent, maybe with better instructions, a simpler assembly, let's say we don't change the average, but we can just reduce the uncertainty, we might be able to say, hey, this is going to take anywhere between 4 and 16 minutes. So we can reduce and be more consistent when we can reduce variability. So that's the importance of this. Let's also, by far, what's always important, what we're going to use the normal distribution to do is solve for areas under a curve. The blue on this spreadsheet is the area under the curve, and that is a cumulative distribution. So right now I have it set up that if x is equal to 25, which is way out here, what's the probability that the area under the curve, or the probability that I'm going to get a number less than or equal to 25. That's everything to the left. And you can see that's practically all the area. look at the formula that I use. In the normal distribution, we're going to use this formula in Excel, the norm.dist, and it takes 4 arguments. It takes a value on the horizontal axis that we want to find the area to the left. That's what x is. We have to know the mean, the standard deviation, and then we always want to use the argument 1. The 1 tells us we're wanting a cumulative distribution, which is the area to the left. So let's do a little bit more practical problem. What if I put in, let's say we have something centered at 10 with a standard deviation of 2, and I want to know the probability of the area being less than or equal to 10. So I want to know what the area under the curve if my horizontal axis is equal to 10. Well, notice that's the mean, so the area to the left of 10 is 50%. The probability of getting 10 or less is 50%. Remember, this is a symmetrical distribution. Now, remember, the total area has to sum to 1. That's what makes a probability distribution. But because of that, then the area to the right, in this case, is also 0.5. If I want to say what's the probability of getting something less than or equal to 13. So 13 is about right there. We could ballpark it, and it looks like it's about 80-90% when I hit 13. The area to the left of that is 93%. So the probability that x is greater than 13 is going to be equal to 1 minus the area to the left. That's how we calculate areas to the right, because the total area always has to sum to 1. That's one of the rules we rely on in probability distributions. So the formula that I coded up on this is using the norm dist. The norm dist. The first argument is the area is your x-axis, the value on the horizontal axis that you want to find the area to the left. And then the mean and the standard deviation are the second arguments. And then the last argument, again, always use 1. If you use 0, all you're getting is a point on this red line, and that doesn't do us much. We always are looking for areas, which are cumulative distribution numbers. Okay, we'll have some more videos on of how to use this to solve some problems, and then we'll talk about some special types of normal distributions and the central limit theorem. Thanks.